Imagine you're standing in a wide-open field, the sun shining gently on your face. You're holding a simple rubber ball in your hand, feeling its smooth surface and anticipating the simple act you're about to perform. Now picture this. In front of you stands a tall, solid brick wall, an imposing structure that seems to stretch endlessly. This wall isn't just any barrier, it's a symbol of the predictable, reliable rules of our everyday world, the world we experience with our senses. With a gentle toss, you throw the ball directly at the wall. It's a simple action governed by the laws of physics we've come to understand so well. Predictably, it bounces back every single time. The ball hits the unyielding surface and rebounds, a testament to the solid, impenetrable nature of the wall. There's no surprise, no deviation from the expected outcome. This is classical physics in action. Objects need a certain amount of energy to overcome barriers. The ball simply doesn't possess enough energy to break through or bypass the wall. No energy, no passage. It's a fundamental principle that governs our macroscopic world. A car, no matter how powerful, can't simply drive through a mountain. The mountain presents an insurmountable barrier. Similarly, a person can't just walk through a locked door. The lock and the solid material of the door prevent passage. The rules are clear, the boundaries are well defined, and the outcomes are predictable. The wall is simply too strong, too solid, and the ball, in comparison, is not strong enough to overcome it. That's our everyday reality, the world governed by the familiar laws of physics. But what if I told you there's another realm, a hidden world operating beneath our senses, a reality far stranger and more fascinating than we can readily perceive? Welcome to the quantum world, the realm of atoms, the fundamental building blocks of matter. Here, we explore electrons and all the other fundamental particles that make up everything we see and touch. In this realm, certainty dissolves into a sea of possibility. Definite locations become probabilities and the very nature of reality shifts. The rules change, the laws of physics as we know them are bent and sometimes broken. At this incredibly small scale, the wall isn't an absolute stop sign, an impenetrable barrier. And the ball isn't just a simple solid object, it's a complex quantum entity with wave-like properties. Now imagine you throw a quantum ball, like an electron, at a quantum wall, a barrier at the atomic level. Prepare yourself because something truly bizarre, something seemingly impossible can happen. Most of the time, just like the rubber ball, it bounces back, reflecting off the barrier as expected. But sometimes, without any extra energy being added, without any apparent force, the electron, defying all expectations, simply appears on the other side of the wall. It doesn't break the wall, it doesn't blast through with brute force. It just is there, as if it teleported through the seemingly impenetrable barrier. This isn't magic, a trick of the light, or some fanciful illusion. It's a real, scientifically proven phenomenon known as quantum tunneling. The universe at its smallest scales is far stranger, far more unpredictable, and far more wondrous than we ever could have imagined. The wall, once a symbol of absolute limitation, is no longer a barrier in the quantum realm. Instead, it's a gateway, a passage to the seemingly impossible, a glimpse into the hidden potential of reality. Welcome to the quantum world, where the rules you thought you knew are constantly being rewritten, where the very fabric of reality is transformed. This mind-bending phenomenon is quantum tunneling, a cornerstone of the quantum world. How can a particle perform this seemingly impossible act? How can something just pass through a solid barrier? It defies our everyday understanding of how the world works. The answer lies in the bizarre nature of the quantum world, where particles aren't just particles, they also behave as waves. This duality is key to understanding quantum tunneling. An electron, for example, isn't just a point-like object with a specific location. Instead, it exists as a wave of probability, a mathematical description called a wave function. This function spreads out, describing the likelihood of finding the electron at any given point in space. This wave doesn't tell us exactly where the particle, but rather describes where the particle be found, if we were to look for it. Where the wave is high, there's a high chance of finding the particle. Conversely, where the wave is low, there's a low chance. So until you actually measure its position, the particle exists as a fuzzy cloud of possibilities, spread out according to its wave function. Now let's go back to our wall. A classical ball, like a tennis ball, has a definite position. Its location is certain and predictable. It will either bounce off the wall or be stopped by it. It never appears on the other side, inside, or beyond the wall. But a quantum electron's wave function behaves in a fundamentally different way when it encounters a barrier. When the electron's wave function hits a barrier, the majority of the wave is indeed reflected back. However, a faint but crucial part of the wave manages to leak through the barrier. This leakage is the essence, the very heart of quantum tunneling. It means that a tiny piece of the electron's wave function extends to the other side of the wall. This implies that there's a small, but non-zero, probability that when we look for the electron, it will be found on the other side of the barrier. And when you perform a measurement, the wave collapses, forcing the electron to choose a single, definite location. And sometimes, against all classical intuition, that location is on the far side of the wall. The particle didn't magically break the laws of physics. Instead, it cleverly exploited the inherent uncertainty that is built into the very foundation of its existence. Quantum tunneling, therefore, is a kind of leap of faith, a probabilistic jump that is woven into the very fabric of reality at the quantum level. It's important to understand that it's not teleportation, nor is it some kind of magical trick. Rather, it's the natural and inevitable consequence of a particle existing as both a particle and a wave simultaneously. The seemingly impossible becomes possible, not through brute force but through the subtle power of probability. This, in essence, is the quantum leap. A particle's wave nature allows it to exist, however briefly, in a place where it classically shouldn't be. The universe, at its most fundamental level, is not a collection of certainties, but a realm of shimmering possibilities, waiting to be realized. And sometimes, just sometimes, those possibilities, against all odds, become real, shaping the world around us in profound and unexpected ways. To understand the seemingly bizarre phenomenon of quantum tunneling, let's first consider something more familiar: sound. We'll use an analogy to bridge the gap between our everyday experiences and the counterintuitive world of quantum mechanics. Imagine you're in your apartment and music playing next door leaks through a wall. You don't hear the full blast of the music, but rather faint, muffled vibrations. The wall acts as a barrier, reducing the sound's intensity. Similarly, in the quantum realm, a quantum wave function is a wave of probability, a mathematical description of where a particle is likely to be found. It's not a precise location but a probability distribution, mapping where a particle could be at any given moment. When this wave encounters a barrier, like a force field or an energy potential, most of it reflects, bouncing back as if hitting a wall. However, unlike a solid object, a small fading tail of the wave penetrates the wall. The thicker or higher the barrier, meaning the more energy it takes to overcome it, the fainter this whisper becomes, the less likely the particle is to tunnel through. For large objects like a basketball, something composed of countless atoms, the odds of tunneling are so astronomically tiny they're effectively zero. We'll never see a basketball pass through a wall. But for a single electron, a fundamental particle, and a thin barrier, one at the atomic scale, that seemingly small chance, that tiny whisper, becomes statistically significant. Quantum tunneling isn't a certainty, but a game of odds, a roll of the dice in the quantum casino. And for particles, the seemingly impossible becomes inevitable over countless tries, over vast numbers of interactions. The particle isn't consciously choosing to tunnel, it's not making a decision. Rather, its inherent wave nature means that sometimes it simply appears on the other side of the barrier as if by magic. At the smallest scales, reality is a place where solid objects as we perceive them dissolve into waves of pure potential, governed by the laws of quantum mechanics. The rules of the quantum world may seem strange and counterintuitive, but they're undeniably real, and they govern the behavior of everything at the most fundamental level. Tunneling isn't just some obscure theoretical concept, it's a fundamental feature of our universe, a key mechanism in many natural processes. In the quantum world, the impossible is just another possibility, waiting for the right conditions to manifest. Picture a flowing ribbon, the electron's probability wave approaching a steep hill, our energy barrier. Most of the ribbon folds back, showing high reflection, but a faint strand slips into the hill, shrinking as it goes. This is the wave function decaying exponentially, a ghostly presence inside the forbidden zone. If the barrier isn't too wide, that faint strand emerges on the other side, thinner but real. It continues as a smaller wave, representing a real chance of finding the particle beyond the barrier. The journey of the wave function is the soul of quantum tunneling. The particle doesn't dig or break through, its wave nature lets it exist in multiple places at once. The universe has a loophole for the impossible. Quantum tunneling is a beautiful, elegant, and utterly strange phenomenon, It's the whisper of possibility crossing the divide. Quantum tunneling isn't just theory, it shapes our universe. Take radioactive decay, the process that powers stars and lets us date ancient artifacts. Inside a heavy nucleus like uranium, particles are trapped by the strong nuclear force, a nearly impenetrable wall. An alpha particle rattles inside, unable to escape by classical rules. Yet, uranium atoms do decay, spitting out alpha particles. How? Quantum tunneling. The alpha particle's wave function leaks through the nuclear barrier, though the odds are tiny, but it tries billions of times a second. Eventually, it tunnels out. This makes radioactive decay a probabilistic process. We can't predict when, only the odds. Some elements have barriers so strong their half-lives are billions of years, others decay quickly. Without tunneling, elements forged in stars would be locked away forever. The universe's dynamism depends on this quantum ghost slipping through atomic walls. Tunneling is the key to cosmic change. Quantum tunneling has given us superpowers like seeing individual atoms. Traditional microscopes can't resolve atoms, their light is too thick. Enter the scanning tunneling microscope, or STM, invented in the 1980s. The STM uses a sharp metal tip brought within a few atoms' width of a surface separated by a vacuum gap. Classically, electrons can't cross this gap, but quantum tunneling lets a few slip through, creating a tiny current. This tunneling current is exquisitely sensitive to distance. Move the tip a fraction of an atom, and the current changes dramatically. By scanning the tip and keeping the current constant, a computer maps the surface, atom by atom. For the first time, we could see the building blocks of matter. Quantum tunneling turned the invisible world visible. It's a triumph of science and imagination. Quantum tunneling isn't just for microscopes or stars, it powers our technology. As we shrink microchips, we enter a realm where quantum effects dominate. Transistors, the switches of digital electronics, now have barriers just a few atoms thick. Electrons can tunnel through these barriers, causing gate leakage, a challenge for engineers. Sometimes tunneling is a problem, wasting power and generating heat. But in other devices like tunnel diodes, we harness tunneling for high-speed performance. Quantum tunneling is also key to quantum computing, where it enables new kinds of logic and memory. The ghost in the machine is now a tool we're learning to master. Our digital world runs on the strange rules of the quantum. The impossible leap is at the heart of modern life. Why does quantum tunneling matter? Because it reshapes our understanding of reality. It shows us that the universe isn't a rigid machine, but a place of uncertainty and possibility. The same principle that powers the sun also lets us see atoms and build advanced computers. Tunneling connects the cosmic and the microscopic, the stars and our smartphones. It's a universal language, revealing the unity of nature's laws. Embracing tunneling humbles us. It reminds us our intuition is limited. The universe isn't obliged to make sense to us. We must follow the evidence, even through solid walls. Without tunneling, the sun wouldn't shine, heavy elements wouldn't exist, and technology would stall. The leap of a single particle is one of the most important processes in the cosmos. The impossible is woven into everything. Quantum tunneling is why we're here. Particles passing through walls may sound like magic, but it's not. Quantum tunneling is science. Predictable, measurable, and described by quantum mechanics. Its predictions have been tested and confirmed countless times. The quantum world defies common sense but follows strict mathematical logic. Engineers and physicists rely on tunneling to build and use real technologies. The story of tunneling is the story of science, observation, theory, and innovation. The universe's deepest mysteries aren't sealed away, they're puzzles to solve. The next time you use a computer or look at the sun, remember the quantum leap. The impossible is real, and science is our key to understanding it. The cosmos is grander and stranger than we imagine, and science is how we explore it.